Hi everybody, I'm Murray Barnes, the lead developer of VPLanet, and in this video I'm going to describe the physical models that underpin VPLanet and present a specific example. If you watched the introduction to VPLanet video, you saw this slide already, which is the planets are hard diagram, but with arrows that represent the different modules that are available in August of 2023. Each module is a collection of equations that describes a specific aspect of planetary system evolution. Assembling the modules defines the physics of the code, and so in many ways this is the most fundamental aspect of VPLanet. So to begin, I want to make a clear distinction between models and modules. A module represents a physical process that can occur in a planetary system, such as atmospheric escape, which is controlled by the ATMESC module. The models, on the other hand, are the physics equations that describe the evolution of the system. Modules can include many unique models inside of them. For example, atmospheric escape can be due to processes like Roche-Loeb overflow, energy-limited escape, diffusion-limited escape, and others. The user chooses the modules and their models at runtime. So in other words, the user creates input files that specify the module, the models, and the initial model parameters. Many modules can be coupled. For example, the tidal dissipation with the ectide module and stellar evolution with the stellar module. To see which phenomena have been coupled within the code, check the examples in the GitHub repository. Models currently consist of coupled ordinary differential equations, partial differential equations, and/or the interpolation of previously simulated and published results. All right, so now let's get into the different modules that are available as of August 2023. First up is Thermit, which stands for Thermal Interior Evolution. This module simulates the thermal evolution of terrestrial planet cores and mantles, as well as the generation of the magnetic dynamo in the core. This module is largely derived from papers from Driscoll and Bercovici and has been calibrated to Earth and Venus. For each of the modules, the primary developers are listed too. In this case, it's Peter Driscoll and Rudy Garcia. Next up is RADHEAT, which stands for Radiogenic Heating. This module tracks the heating of planetary interiors by the radioactive decay of isotopes like aluminum-26, potassium-40, thorium-232, uranium-235, and uranium-238. This module splits the planet into the core, mantle, and crust, tracking the power generated in each. Next up is MAGMOC, which simulates the thermal and geochemical evolution of the magma ocean, including the surface fluxes of oxygen and water, as well as the oxidation of iron in the interior. MAGMOC is largely a mixture of the Elkins-Tanton 2008 and Schaefer et al. 2016 models. Note, this module was not part of the original VPLanet package and is instead described in this paper led by Patrick Barth. Moving on, the Distorb module contains semi-analytic models of the orbital evolution of multi-planet systems. The models were developed centuries ago, but VPLanet incorporates the methods described in the paper from Ellis and Murray in the year 2000. This module includes both the second-order eigenvalue solution as well as the fourth-order secular evolution solution, and it also includes general relativity. Next up is Distraught, which is similar to Distorb, but handles the rotation. This module accounts for the evolution of a planet's spin axis relative to its orbital plane due to the evolution induced by companion planets as well as the torque from the central body. Most of this theory was developed by Jacques Lescar and collaborators in 1993. And note that this module can also read in pre-computed orbital parameters. Next is Spin Body, which calculates the positional evolution of bodies due to their mutual gravitational interaction and is derived from first principles. The goal for this module is to also calculate the direct torques between bodies, but this phenomena has yet to be incorporated. The next module is Binary, which simulates the orbital evolution of a circumbinary planet. Like Distorb, it's a semi-analytic model, but is limited to just a single planet. This model is taken from a paper that came out in 2013 by Liu and Li. Next is Ectide, which calculates the effects of equilibrium tides. This module tracks how the deformation of an object due to the perturbations of a nearby body will modify the orbital and rotational properties of the two bodies, as well as their internal heating. In this case, we've largely incorporated models from Faraz-Malo and collaborators, as well as the Kant et al. In 2010. This module includes both the constant phase lag model, sometimes referred to as the tidal Q model, as well as the constant time lag model. POISE, which stands for the Planetary Orbit Influence Simple EBM, is a one-dimensional climate model that tracks surface temperature and ice sheets on Earth-like exoplanets. This module largely incorporates the work of North and Coakley and Hybers and Zipperman. Next up is Galabit, which is short for Galactic Habitability. This module tracks the orbital evolution of a wide binary star due to the galactic tide and passing stars. Changes to the star's orbit can modify the planetary orbits. This module also accounts for radial migration, the distribution of stellar masses, and the radial density gradient of stars in the galaxy. ATMESC, or atmospheric escape, tracks atmospheric loss due to Roche lobe overflow, radiation recombination limited escape, energy limited escape, and diffusion limited escape. Many people have worked on this problem over the last 50 years, and here are a few papers from which we derive our models. Also note that this module includes water photolysis and oxygen escape via hydrodynamic drag. Stellar is our stellar evolution module, which tracks bulk properties, such as luminosity, structural evolution, radius, etc. Stars can be simulated from their birth to thermonuclear ignition to the end of the main sequence. This module also tracks magnetic braking and XUV evolution as well. And finally, the last module available in August 2023 is the FLARE module, which tracks the XUV emission from stellar flares following the empirical relationship from Jim Davenport and collaborators from 2019. This module was also developed after the initial VPLanet paper and is described in Laura Amaral's 2022 paper. Now, an important aspect of VPLanet is that many of these modules can be coupled together. So as an example, I'm going to describe the habitable evaporated core example in the GitHub repository. This example tracks the evolution of a gaseous planet into a habitable planet due to the escape of hydrogen, which is driven by the XUV luminosity of the star. In addition, this example includes the tidal evolution of the star-planet pair. Thus, we have a system that consists of two objects that interact with each other, the star and the planet. The star evolves due to both the tidal torque and its natural stellar evolution. Therefore, the star must use the stellar and ektide modules. The planet is, of course, not a star, so it does not need the stellar module, but instead needs the atmospheric escape module ATMESC. And since it is also tidally evolving, it also needs the ektide module. So clearly, our simulation must include these three modules, but each object only needs two of them. Schematically, the model looks something like this. Here, VPLanet in the center controls the stellar, ektide, and atmospheric modules. At this stage, we've only determined which processes are relevant to which bodies in our system, but we haven't yet chosen which individual models that will predict the evolution. So let's talk about them next. Each module could contain one or more models for parameter evolution, and you should check the documentation to see which models are available for each module. In this case, we have the following possibilities. ATMESC has models for the escape regime, the water loss mechanism, water's XUV absorption, and an envelope radius model. Stellar has models for the XUV evolution, its bulk properties, and magnetic braking. Ektide only has one possibility, and that's the tidal model. So if we expand our schematic to include the models, it would look something like this, where you can now see how each of these modules has additional ways to break down the physics that will be simulated. This diagram is exactly the same information as in the previous slide, it's now just in graphical form. The final step, therefore, is to select the specific models we want to incorporate into our simulation. In other words, which XUV model do we want to use? Which atmospheric escape model do we want to use? Etc. And again, this is something that varies on a case-by-case basis. You'll need to check the documentation to see what's available. So rather than just list all the possibilities here, let's move right on to the complete schematic of all the possibilities. Now we see the full breadth of permutations of models that we could explore and compare against each other to determine the differences between their predictions and maybe even validate one or more of them that fail to reproduce observations. Please note then that the total number of physical models you can simulate with VPLanet is much larger than the number of unique module combinations. There are already thousands of different possibilities you can explore with VPLanet. In the habitable evaporated core example, we only can consider a subset of these possibilities. So for example, the star uses the stellar and ektide modules, and in one trial in the example, the XUV model is set to the Rebus et al. Empirical model from 2005. For the bulk properties, we can use the Baroff et al. 2015 model grids, and for magnetic braking, we can use the Matt et al. 2015 model. For ektide, let's use the constant time lag model. The planet, of course, uses a different set of modules. The ektide module requires the same model to be applied to all bodies, so we have to continue to use the constant time lag model. For the radius, we can use the envelope model grids from Eric Lopez and collaborators. Water's XUV opacity can be dependent on the XUV flux as described in Beaumont et al. We'll use the Luger and Barr's 2015 water loss scheme, and the escape will be energy limited. These choices are just examples, and you can and probably should try other possibilities. And that's indeed what's done in the habitable evaporated core example. which contains simulations of Proxima Centauri b. On the left is the figure that is generated in that example. First, the different quantities that are plotted over time and that are related to the three modules are shown. In some cases, the different modules produce different outcomes. For example, the escape model predicts different envelope mass evolution for the energy-limited escape, the radiation recombination-limited escape, as well as the automatic model, which determines the evolution based on the instantaneous properties of the planet and the system. So what did VPLanet do here? First, it read in the input files and assembled the equations from user instructions. In this case, it was a total of 3 files, one for each object, as well as the primary input file that provides top-level instructions. The code then simulates the evolution of the system by simultaneously solving the set of ordinary differential equations that were chosen by the user, the models. VPLanet simulates the system via a fourth-order Runge-Kutta integration method with a dynamically chosen time step. The code then writes out the time series values of user-selected parameters. In other words, in the input files, you select which parameters you would like the code to output to a file. And finally, in this case, we use vplot to generate a publication-ready plot. All right, this concludes your introduction to the VPLanet model. If you'd like more information on this example, you can go to the website, which is part of the VPLanet repository. Don't forget there is significant documentation on that website, as well as additional videos online that describe other aspects of how to use VPLanet, such as installation and performing parameter sweeps. Thanks for watching, everybody, and good luck simulating those habitable worlds.